Welcome back, viewers. Before we go into today's exercises, I would like us to recall the following sets. The set E, which is equal to the collection of 0, 2, 4, 6, and so on. This is nothing but the set of R2K, so that K is in the set of natural numbers, union 0, 0, which are also require the set O. This is the set of even numbers. Then we look at the set of odd numbers, 1, 3, 5, 7, which is equal to the set of all 2K plus, let me say, 2M plus 1, so that M is in the set of natural numbers, union 0. These two sets, the properties of these two sets will play an important role in what we do. And that property is the following. I want us to observe that if P is an even number, if P is an even number, then by the definition above, there exists K in the set of natural numbers, union 0, such that P is equal to 2K. This is equal to 2K. Now, if we square P, we get that P squared will be equal to 2K all squared. This will give us 4K squared, which we can rewrite as 2 into 2K squared. So that certain T equal to 2K squared, we see that T is in N union 0, and then that P squared will be equal to 2T. What this means is therefore, that, meaning that P squared is an even number. This means therefore that P, an even number, implies that P squared is also an even number. Whenever P is an even number, we get that P squared is even number. The same argument holds for the odd numbers. For if same Q is an odd number, if Q is an odd number, then there exists M in N union 0, such that Q is equal to 2M plus 1. This therefore means that Q squared is equal to 2M plus 1 all squared. And this will give us 4M squared plus 4M plus 1. And this further can be written as 2 into 2M squared plus 2M then plus 1. Meaning therefore that if we set say S equal to 2M squared plus 2M, then S belongs to the set of natural numbers union 0, and Q squared would then be 2S plus 1. This again means therefore that Q squared is an odd number. So what we had is therefore that Q, an odd number, implies that Q squared is also an odd number. Remember that we use O to represent the set of odd numbers. So whenever we take an odd number, each square is again an odd number. And whenever we take an even number, then each square is also an even number. The converse of what we've done above also hold, in the sense that if say R is a number, so that R squared is an even number. If R is a number, so that if R is so that R squared is even, then R is also an even number. An even number. And then if say A is so that A squared is an odd number, then A itself is also an odd number. Is an odd number. Is an odd number. So these explanations will guide us in the following exercise. And what is that exercise? The exercise very starts. I want us to prove that square root of 2 is not a rational number. Remember that Q represents a set of rational numbers. And we remember that the set of rational numbers, Q, is equal to the collection of all P over Q, so that P and Q are integers. P and Q are integers, but with Q not equal to 0. So this is the set of integer. We want to show that root 2 is not a rational number. Now, if we're able to show that root 2 is not a rational number, this will mean that if we eventually get that root 2 is a real number, it means that the set of rational numbers is a proper subset of the set of real numbers, meaning that the set of real numbers contain more points than the set of rational numbers. So let us try to see if we can justify this. Proof. We'll go thus. Suppose for contradiction that root 2 is a rational number. Suppose for contradiction that root 2 is a rational number. Then there exists P, Q in the set of integers. PQ in Z such with Q not equal to 0, such that root 2 is equal to P over Q, meaning that every rational number can be expressed as in the form of this quotient, in this form, where P and Q are integers with Q not equal to 0. So if we assume that root 2 is a rational number, it means that we can find two integers with one of them with Q not equal to 0, so that root 2 can be written in this form. Here we shall assume without loss of reality that P, Q have no common divisor. They do not have common divisors, because even if they had common divisors, those divisors will cancel out themselves. So we assume that P and Q do not have common divisors. Now, with that assumption, we now have that root 2 equals P over Q gives us therefore that 2 will be equal to P squared over Q squared, which is equivalent to saying that p squared is equal to 2q squared. And what does this mean? Remember that q is an integer and q is not equal to 0. Therefore, q squared will be really positive, meaning that q squared is a natural number. And if q squared is a natural number, it therefore means that having written p squared as 2 times a natural number, then it means that p squared is an even number. So this implies, thus, we obtain that p squared is an even number. P squared is an even number. This therefore means that there exists a value k in the set of natural numbers union say 0 such that p squared is equal to 2k, so that p squared is equal to 2. So p squared is an even number, sorry. Yes, this is a true statement, but that is not really what I want. What I want is that since p squared is an even number, then we have that p itself is also an even number. So what we have is that p squared is an even number. Thus, p squared is an even number, and so p itself is also even. Is also an even number. Therefore, there exists k in the set of natural numbers union 0 such that p is equal to 2k, since p is an even number. This means therefore that this implies therefore that p squared is equal to 2k all squared, and this will give us 4k squared. What does this therefore mean? Since we have that p squared is equal to 2p squared, and here we're getting that p squared is equal to 4k squared, we have therefore that 2q squared is equal to 4k squared, which in turn gives us that q squared is equal to 2k squared. This again means that q squared is an even number. So q squared is an even number. And this implies that q is also an even number. So q is also an even number. So what have we gotten? What we've gotten is that if we assume that root 2 can be written as p over q, where p and q are integers, with q not equal to 0 and p and q not having common divisors, we ended up getting that both p and q are even numbers, which means that p and q have common divisors, and this is a contradiction. So what we had is that p and q are an even and thus had common divisors. This is contradictory since we assumed without loss of generality that p and q do not have common divisors. Hence, what we can conclude here is that root 2 is not a rational number. Root 2 is not in Q. So meaning that we cannot express root 2 as exact fraction or ratios. And that is that we also cannot express root 2 as a number with recurring decimal points. So root 2 is not a rational number. And that is what we've been able to get in this exercise. The next exercise will show us that we can find a number, a real number, whose value is equal to root 2, meaning that root 2 belongs to R. So, here we shall prove that there exists M in the set of real numbers such that M is equal to root 2. So this is what we want to show, that we can find a real number whose value is equal to root 2. So let us try to do that. To do this, we proceed as follows. I'll build a little construction, and that construction is as follows. We shall set a set, we shall construct a set I'll call, say, X. So set X to be equal to the collection of all X in R so that X squared is less than 2. I set X to be the collection of all X in R so that X squared is less than 2. It is obvious that X is well defined since numbers like 0 and 1 belong to X. The reason is clear. 0 squared is 0, which is really less than 2, and 1 squared is 1, which is really less than 2. So 0 and 1 belongs to X. So X, that is to say, we have therefore that X is not an empty set. This is what we mean by X being well defined. Next, I will claim, let me call this, I don't know the number of claims we may have, but let me call this claim 1. Claim 1 is that X is bounded above by 2. And if we're able to get that X is bounded above by 2, it means that X is a bounded set. And thus, X must have a supremum. I mean, X is bounded above means that X is bounded above by 2 means that X is bounded above and therefore must have a supremum. We call this supremum, say, gamma naught. Now, if we call it gamma naught, our target is to get that this supremum will do the job. We'll get that, we'll try to show that that supremum gamma naught, if we call it gamma naught, will end up being square root of 2. So if we get that is equal to square root of 2, we will now choose this term we are looking for to be that gamma naught, and that will complete the proof. So here, X is a bounded above by 2 is what we'll try to justify now. So to see this, we assume for contradiction that X is not bounded above by 2. That say there exists um, x naught in x such that um, x naught is greater than 2. Remember that x bounded above by 2 means that for any x, we pick in x, x must be less or equal to 2. So that x is not bounded above, if we assume for condition that x is not bounded above by 2, what it means is that there exists a certain x naught in x, so that x naught is bigger than 2. That is what I put down here. So, but x naught bigger than 2 implies that x naught squared is bigger than 4. That is, x naught squared will be bigger than 4 squared. So we have therefore that x naught squared is bigger than 4 and this 4 is bigger than 2. So this implies that x naught squared is bigger than 2, which is a contradiction. This is a contradiction. What is it contradicted? So this is a contradiction. What is it contradicting? It contradicts the fact that x belongs to x. X naught belongs to x. As since x naught belongs to x must be one of those x in R so that x squared is really less than 2. But here what we are getting is that x naught squared is bigger than 2, which contradicts this inequality. Therefore, our conclusion here is therefore that the set x is bounded above by 2. Thus, so supremum of x exists. Supremum of x exists. If we let, say, gamma naught be equal to the supremum of x, if we let gamma naught equals supremum of x, if we let gamma naught be equal to the supremum of x, we have the following claim to make. We claim, this is claim 2 we are meeting. We claim that gamma naught is equal to the square root of 2. We claim that gamma naught is square root of 2. Now, supposing proof of claim 2, suppose form contradiction that gamma naught is not equal to root 2. If we assume for contradiction that gamma naught is not equal to root 2, then two cases arise. And these two cases are as follows. Either gamma naught is really less than root 2 or gamma naught is bigger than root 2. So these are the two possibilities. Since gamma naught is not equal to root 2, it means that gamma naught will either be less than root 2 or gamma naught is bigger than root 2. Let me see. So let gamma naught be equal to this. We claim 2 gamma naught squared is equal to 2. Gamma naught squared is equal to 2. To prove this, we proof of claim 2, we suppose for contradiction that gamma naught squared is not equal to 2. Then either gamma naught squared is less than 2, or gamma naught squared is greater than 2. Now, if gamma naught squared is less than 2, then 2 minus gamma naught squared will be bigger than 0. This is what we'll get. Now, let epsilon greater than 0 be given when compute as follows. So, given a positive number, we compute as follows. What are we computing? We shall look at say gamma naught plus epsilon squared, and this will give us gamma naught squared plus 2 gamma naught epsilon plus epsilon squared. So this is what we'll get. What am I trying to achieve? The idea here is that we assume that gamma naught squared is less than 2. Remember, we are assuming for contradiction that gamma naught squared is not equal to 2. So this led to having that either gamma naught squared is 2 or gamma naught squared is bigger than 2. So our assumption that gamma naught squared is less than 2, we expect this to lead us to a contradiction, meaning that this would fail. And next, we'll pick up on this and also show that it leads to a contradiction, meaning that this also fails. So if these two fail, it will mean therefore that this assumption is not true. And what would then be true is that gamma naught squared will be equal to 2. That's the idea of what we are doing. So here, I'm taking epsilon bigger than 0 is to compute this gamma naught plus epsilon squared. If we do gamma naught plus epsilon squared, and we're able to get that this particular thing is less than 2 for a certain range of epsilon, then that will contradict the fact that gamma naught is the supremum of the set, of this particular set, X, because we've gotten something that is more than gamma naught that will still be a member of this set. If we're able to get that gamma naught plus epsilon squared is less than 2 for a certain range of epsilon. So let us walk through and see what we'll get. Now, observe that this is still equal to gamma naught squared plus, I say 2 gamma naught plus epsilon, then times epsilon. Now, if epsilon is less than 1, then let me label here, say star. Then we'll obtain from star that gamma naught plus epsilon all squared will be, of course, equal to gamma naught squared plus 2 gamma naught plus epsilon, then times epsilon. And this will be less than gamma naught squared plus 2 gamma naught plus epsilon. Sorry, please. This will be. Let me explain this. We have to be very, very careful here. There is a way you put up this estimate, it will put you in trouble, and that is what that has just happened now. I went at the estimated wrongly. This particular one will be the key that will guide me, to help me get what I'm looking for. And I quickly went, and not that what I did is wrong, but I am sort of too fast in controlling this one. So what I should have controlled is this one inside, controlling it by this particular this assumption. So if I control this one will be left open to be used for another possible control. So if I handle this one, not that it's wrong, but it will not really give me what I want. It's good that we explain this so that people will understand that what we are doing doesn't fall from heaven. You must practice before you get acquainted with what is happening. So I just observed that where I apply this is wrong. So our ladder will not give me what I want. So what I'll do is to go back and apply it in such a way that I'll get what I really want to get. And to do that, we'll return to this. So what I'll do is the following. So let us watch. So this will be less than 2 gamma naught plus 1, then times epsilon. So you see, this one is the one that brought about this inequality because this is assumed to be less than 1. This particular one now will help us sort of handle there in a special way. Now remember, when I was doing exercises, when we did some exercises on biological that had to do with absolute value functions, you'll find out that you'll remember that I started putting up certain controls. So what shall we put as a control in such a way that something becomes less than epsilon? I think I did this severally. The essence of that is preparing our mind to towards meeting this kind of problem. So what I will then do here is what range of value will epsilon be so that what I'm looking for will happen. Now watch and see what I'll do now. And here I'll use the fact that this particular thing is bigger than 0. And what I want to do is to remove this thing and get something here that by the time we simplify it, I'll get 2 on this side. So that will give me that this thing is less than 2. And when I get that this is less than 2, it means that for the particular range of epsilon positive, I've gotten that gamma naught plus epsilon all squared is less than 2. And that contradicts the fact that gamma naught is the supremum of that particular set, of the set X above, of this set X, of this set. So let us do it. Now, at this junction, if epsilon is less than what here, I'll use the fact that this is bigger than 0 and the fact that this particular thing is also bigger than 0 to get the control, that is the range. The second, remember we've already put this condition on epsilon. We want to put another condition on epsilon. And the second condition I want to put on epsilon is the following. I want to have, if epsilon is less than 2 minus gamma naught squared all over 2 gamma naught plus 1, if epsilon is less than this quotient. Let me call him, say, star, star. Then we obtain from and star, star, that and gamma naught plus epsilon all squared will be less than gamma naught squared plus 2 gamma naught plus 1, then into 2 minus gamma naught squared all over 2 gamma naught plus 1. This is what we'll get. But of course, we'll now see that this 2 gamma naught plus 1 will cancel this 2 gamma naught plus 1. So that what remains will be that that what we have will now be equal to gamma naught squared plus 2 minus gamma naught squared. And this is nothing but 2. So what I have therefore is that if epsilon is less than 1, and then if epsilon is less than 2 minus gamma naught squared over 2 gamma naught plus 1, then gamma naught plus 1 plus epsilon all squared will be less than 2. How do I might these two? If epsilon is less than 1 and if epsilon is less than this, putting them together will give me therefore that if epsilon greater than 0 is less than the minimum of 1 and 2 minus gamma naught squared over 2 gamma naught plus 1, then, now watch here. If epsilon is less than the minimum of these two, minimum of them is the smaller of the two. So if it's less than the smaller of the two, then definitely it's less than also whichever one that is bigger. And this will mean that epsilon is less than both of them. So if epsilon is less than 1 and if epsilon is less than this, can be expressed, can be captured by what I've just written here. Then, remember that epsilon is bigger than 0, and the fact that this is bigger than 0 means that this, if epsilon lies between 0 and this entity, then we shall have that what? Gamma naught plus epsilon all squared will be less than 2. And this is what? A contradiction. A contradiction. A contradiction. Why is it a contradiction? Because what this is telling me is that and this means that gamma naught plus epsilon for epsilon that lies between this range, between 0 and this entity, the gamma naught plus epsilon belongs to x. Remember that x is the collection of all x in R, so that x squared is less than 2. So if gamma naught plus epsilon squared is less than 2, it means that gamma naught plus epsilon belongs to this set. And since we have that gamma naught is the supremum of that set, that gamma naught is the supremum of the set, everything in the set must be less than gamma naught because gamma naught is an upper bound. This means in particular that gamma naught plus epsilon will be less than or equal to gamma naught. And of course, this is a contradiction. That is where this contradiction came from, because we have something bigger than gamma naught being less than gamma naught. And this is really a contradiction. This means therefore, what we have is that what led us to this is the assumption that gamma naught squared is less than 2. So therefore, what we have is that gamma naught squared is not less than 2. Now, we shall now look at the other case, which is the case where, remember, we have gamma naught squared is less than 2 or gamma naught squared is bigger than 2. We've already looked at this and found out that this, if we assume that this is true, that this will lead us to this contradiction. Now let us see what will happen if we assume that gamma naught squared is bigger than 2. Now, if gamma naught squared is bigger than 2, let us see what happens. Now, if gamma naught squared is bigger than 2, then we compute as follows. This time around, we shall look at gamma naught minus epsilon all squared. Let us see where this will lead us to. Gamma naught minus epsilon all squared will give us, remember epsilon is any positive number, will give us gamma naught squared minus 2 gamma naught epsilon, then plus epsilon squared. And this, of course, is really bigger than gamma naught squared minus 2 gamma naught times epsilon. So we have therefore that gamma naught minus epsilon all squared is bigger than gamma naught squared minus 2 gamma naught epsilon. Let me letter here small a. Now, if I letter here small a, I want us to observe that gamma naught squared greater than 2 implies that gamma naught squared minus 2 is bigger than 0. And since gamma naught squared minus 2 is bigger than 0. And there's something we did not mention which we shall need now. That is the fact that we assume that, remember that our x is equal to the collection of all x in R, so that x squared is less than 2. Remember that we were able to see that this set is not empty, and we had that 1, for instance, belongs to x. And since 1 belongs to x, and we have that gamma naught is equal to the supremum of x, then this means that 1 is particularly less than or equal to gamma naught, because gamma naught is an upper bound. And since 1 is less than gamma naught, it means therefore that gamma naught is bigger than 0. So this is a fact that we'll make use of right now. It's something we'll make use of right now. So we'll make use of this fact right now. So how do we use it? To make use of it, observe here that we have 2 gamma naught. And I've already gotten that gamma naught squared minus 2 is bigger than 0 on assumption that gamma naught squared is bigger than 2. And therefore, so what I have here is having got that gamma naught is bigger than 0, I have therefore that if epsilon is less than gamma naught squared minus 2 all over 2 gamma naught. All over 2 gamma naught. This makes meaning because we've already seen that gamma naught is bigger than 0. And thus, this question makes meaning. If epsilon is less than this, then this will of course be equivalent to saying that minus epsilon will be bigger than minus gamma naught squared minus 2 all over 2 gamma naught. We'll have that this is true. And this means therefore we shall obtain from A that gamma naught minus epsilon all squared will be bigger than gamma naught minus 2 gamma naught epsilon, gamma naught squared minus 2 gamma naught epsilon, and this is still greater than gamma naught squared, then here we have minus 2 gamma naught. This minus epsilon is bigger than minus this. So this entity here will be bigger than minus 2 gamma naught into gamma naught squared minus 2 all over 2 gamma naught. To see how this happens, you'll find out that I can multiply both sides of this inequality by 2 gamma naught, meaning that minus 2 gamma naught epsilon is bigger than minus 2 gamma naught times this. So adding gamma naught squared to both sides after they multiply both sides by 2 gamma naught, we'll get that this entity is bigger than this entity. But this will give me therefore that from here I'll see that 2 gamma naught will cancel 2 gamma naught. What remains is therefore that gamma naught minus epsilon all squared will be bigger than gamma naught squared minus, of course, gamma naught squared minus 2. And this will give us nothing but 2. Because when we open this bracket, we get minus gamma naught squared plus 2. This will give us this. So what have we got? What we've got is that if epsilon is less than gamma naught squared minus 2 all over 2 gamma naught, then gamma naught minus epsilon all squared will be bigger than 2. So what does this mean? This is again another contradiction. A contradiction. So what makes it a contradiction, or rather what is contradictory about this? What the contradiction is the fact that whenever epsilon is bigger than 0 and less than this entity, that is gamma naught squared minus 2 all over 2 gamma naught, which I get that gamma naught minus epsilon squared will be greater than 2. How is it contradictory? It is contradictory because recalling that I said x is equal to the collection of all x in R, collection of all x in R, collection of all x in R. Sorry, please. Let me do this. Let me repeat it. Remember that x is equal to the collection of all x in R, so that x squared is less than 2. And we remember that gamma naught is the supremum of this set. Gamma naught equals supremum of x. Recall therefore that from our characterization of the supremum of a set, what this means is that once we are given epsilon bigger than 0, assuming that this portion represents the set x, assuming that this portion represents the set x on the real line, then gamma naught is the supremum if here is the gamma naught. Somewhere here, given epsilon bigger than 0, we now move backwards to gamma naught minus epsilon. You remember that characterization says that once you do gamma naught minus epsilon is no longer a lower, is no longer an upper bound. And in that particular case, it means that there is a certain element of the set x that lies between gamma naught and the gamma naught minus epsilon, in the sense that we'll have that gamma naught minus epsilon will be less than x epsilon less than or equal to gamma naught. This is from one of the characterizations of the supremum of a set. So that is bounded above. Given that gamma naught is the supremum of that set, then for all epsilon bigger than 0, there exists x epsilon in the set x, so that this will happen. Now, having got that gamma naught minus epsilon all squared is greater than 2 for all epsilon that lies within this range, what this will lead us to is the following. This will mean therefore that remember our assumption is that gamma naught is spread is greater than 2. So from here, what we shall get from here is that, watch and see what I'll do. What we'll get from here is that gamma naught squared will be bigger than or equal to x epsilon squared, which is really bigger than gamma naught minus epsilon all squared. And from this, with epsilon lying in this within this range, we'll get that this thing is greater than 2. And this means that x epsilon squared is bigger than 2. And this is that contradiction, which is a contradiction. A contradiction. Why is this a contradiction? It is a contradiction because x epsilon belongs to this set, meaning that x epsilon squared must be less than 2. But with this, we have that x epsilon squared is bigger than 2, contradicting the fact that x epsilon is coming from this set. So that is where this contradiction we are pointing out here, we are talking about here, comes from. So let me demarcate this. So that is where the contradiction comes from. So what this leads to is therefore, what we had is therefore that therefore gamma naught squared is not greater than 2. So what have we achieved? We've assumed that gamma naught greater than 2 led us to this contradiction. And we've also seen above that gamma naught squared less than 2 also led to a contradiction. Therefore, hence, the conclusion must be that gamma naught squared is equal to 2. And if gamma naught squared is equal to 2, this is therefore gamma naught is equal to square root of 2. So, meaning that gamma naught is square root of 2. Thus, so choosing gamma naught equal to m, we obtain therefore that there exists m in the set of real numbers such that m is equal to root 2. And this completes the proof. This completes the proof of that exercise. The next exercise I will do has to do with the one interesting property of the set of natural numbers. This I will call exercise 3. What does this exercise say? This exercise says that for any x we pick in the set of real numbers, there exists a certain natural number n depending on x such that n sub x is bigger than x. And this is actually what we call the Archimedean property of the set of natural numbers. That whenever you're given any real number, we can find a natural number that is bigger than that real number. We call it the Archimedean property. So now, what this is telling us invariably is that the set of natural numbers is not bounded above. But the set of natural numbers is not bounded above. Now, to prove this, so we want to show that this is true. Let me fix it here. We prove that for any x in the set of real numbers, there exists a natural number, so that natural number is bigger than this x. And this is part of why I did the existential quantifier and the universal quantifier. You remember that lecture? The reason is that when we come to this kind of problem, we try to do the proof for contradiction, expected to get contradiction if we assume that what we are trying to get is not true. And therefore, to get that this is not true, must negate it. And when you negate it, we now use the negation to see where it will lead us to. And if the negation of this statement leads us to something that is contradictory, it means that that negation is not true, that what should be true is this statement. And that is how the procedure which I take in trying to justify all this, which I call the Archimedean property. So, proof, which I suppose for contradiction that this assertion is not true. And that this assertion is not true means that there exists, say, a certain x naught in the set of real numbers such that for any n we pick in the set of natural numbers, n is less or equal to x naught. Meaning that n, the set of natural numbers, is bounded above. Suppose this is the case. Then this means that n is bounded above, and then thus supremum of n exists. That is what this translates to. So if we let, say, gamma naught to be equal to the supremum of the set of natural numbers, assuming it exists with what we've just seen, and then we have that we obtain that for any n in the set of natural numbers, n was the less or equal to gamma naught. This is what we have, because gamma naught being the supremum means that gamma naught is the least upper bound, and therefore gamma naught is upper bound. So this means in particular, for n equals 2, 3, 4, and so on, n must be less or equal to gamma naught. Now watch here. You will find out that for all n in the set of natural numbers, means n equals 1, n could be 1, n could be 2, n could be 3, and so on and so forth. All of them will satisfy this property. Meaning that if I remove the case where n is equal to 1, the remaining must still satisfy this particular inequality. But we know that every natural number n equals to 3 can be written as k plus 1 with k equals 1, 2, 3, and so on. So every natural number from 2 downwards can be expressed in this form. Here k is running from 1, 2, 3, and so on. This means therefore that for k equals 1, 2, 3, and so on, k plus 1 is less or equal to gamma naught. And what do we have from here? What we have from here is therefore that for k equals 1, 2, 3, and so on, k is less or equal to gamma naught minus 1. What does this translate to? K equals 1, 2, 3, and so on. Having given us that k is less or equal to gamma naught plus 1, means therefore that for any k we'll take in the set of natural numbers, k must be less than or equal to gamma naught minus 1. This is a contradiction. A contradiction. And what is it contradicting? It is contradicting the fact that gamma naught is the supremum of the set of natural numbers. Because if since gamma naught is the supremum, it means that gamma naught is the least upper bound. And now we are getting another upper bound for natural numbers, which is gamma naught minus 1. And this gamma naught minus 1 is less than what we call the supremum. Thus, this leads to a contradiction. What this means, therefore, is that m, the set of natural numbers, is not boundary above. Because it's an assumption that n is bounded above that we know that the supremum exists. Therefore, what we add is therefore that for any x in the set of real numbers, there exists mx in the set of natural numbers such that mx is greater than x. And this completely the above. So, this is what we call the Archimedean property. This is what we call the Archimedean property. Okay, now we'll do yet another exercise. And this exercise we make use of this Archimedean property in getting that exercise done. And what will this exercise talk about? This exercise is a very important exercise, even though I call it an exercise, but it's a very important exercise because it will talk about the density of the set of rational numbers as well as the set of irrational numbers on R. The density of the set of rational numbers and the set of irrational numbers on R. So what does the exercise say? I think this is exercise 4. Exercise 4. Here we just show that given what we shall show here is we shall show that given two real numbers, we shall show that given x, y, in R with x less than y, that there exists a rational number R in Q, there exists a rational number so that x is less than R less than y. And then there exists an irrational number, say R prime in Q, that is in the set of irrational numbers, such that x is less than R prime less than y. So what this is telling us is that between any two real numbers, we can find a rational number. And between any two real numbers, we can find an irrational number. And what this means is that the set of rational numbers is dense in R. What does this mean? How does this issue of density of rationals on R came around, what can we do? What can we use as a simple explanation of these facts so that people will understand what we are talking about? Let us recall uh, the the concept of ecology. You remember that because ecology, we talk about uh, uh, checking the population density of a certain species in a given habitat. And one of the methods used in doing that is to use what they call quadrat. They will throw the quadrat in the habitat. And when they get to where the quadrat is just like a rectangular shape, a rectangular figure that is thrown. When they throw it, they go to where it falls and check whether the species in question lies within the place where the quadrat falls. And if it happens that for each throw that is made in that particular habitat, that you find that particular species within the place where the quadrat falls, then you conclude that that particular species is based in that habitat, that ecosystem. So the same thing is what is playing out here with R, the set of real numbers, as the given habitat. And you know that if we throw that rectangle and the force on the real line, that is the external part of a rectangle, and you throw it the force on the real line, what it will actually, if we throw the rectangle on the real line, what it will actually mark out will be an interval, say x. It will mark out an interval, say xy, xy. So that this region is the region that will be covered by the quadrat. So what we are saying is that when that quadrat is thrown on the set of real numbers as the habitat, that we must find a rational number here, and we must also find an irrational number within this place. No matter where you throw it, we must get a rational and we must get an irrational. So meaning that the set of three numbers is densely populated by the rationals, and that the set of real numbers is also densely populated by the irrationals. That is what we mean by the set of rationals and the set of irrationals being dense in R. So let us try to see if we can show that this is true. So how do we go about it? We now proceed as follows. We then start by assuming that the x is, we shall first assume that x is bigger than 0. So, proof. Let us consider two cases. Two cases arise. Case 1 is the case here we assume that x is bigger than 0. We assume that x is bigger than 0. And if this is the case, we have therefore that 0 is less than x less than y. And this will imply therefore that, say, y minus x will become bigger than 0, so that so that 1 over y minus x is bigger than 0. So 1 over y minus x is bigger than 0, and 1 over y minus x is a real number. And therefore, by the Archimedean property, we have therefore, thus, by the exercise we just did, the exercise that I call the Archimedean property, which I have that there exists a real number, there exists the natural number q such that q is bigger than 1 over y minus x. And this, of course, implies that q into y minus x will be bigger than 1. This is what we have. This is what we just got by assuming that x is bigger than 0. That's the question 1. Also, observe that qx is bigger than 0. Reason is because x is bigger than 0 and q is a natural number. Therefore, qx is bigger than 0. So, qx bigger than 0, we again have, for this qx, x is bigger than 0, and for this qx, we have that there exists, say, certain m prime in the set of natural numbers such that n prime is bigger than qx. What does this mean? This means therefore, this setting S equal to the collection of all n in the set of natural numbers such that setting S equal to the collection of all n in the set of natural numbers such that m is greater than qx. If we define a set S to be this, then S is not an empty set because of the existence of a natural number that satisfies this property. So, S is a non-empty subset of the set of natural numbers. And let the intention here that the set of natural numbers has an interesting property which I had not mentioned before. And that property is that the set of natural numbers is what we call well ordered. The set of natural numbers is well ordered. So, for one to understand what they are talking about, one, they search up for the well ordered principle, and to try to look at it and look at, we will see that the set of natural numbers is well ordered. Not for really published the principle. What the principle says in actuality is that every subset of a well-ordered set has a least element, has a variable. So, meaning that S being a non-empty subset of the set of natural numbers, it means therefore that the variable of S exists by the principle I've just mentioned, which is the well-ordered principle. And this is from the fact that the set of natural numbers is well-ordered. So, since S is a non-empty, since S is a subset of M, and S is not empty, is not an empty set. Say space is not an empty set, then it many combinations of S exists. S has a variable. Now, let P be equal to the minimum of S. Let D be the minimum of X. Then, we shall see that if P is the minimum of S, then V minus 1 will be less than or equal to Qx. V minus 1 must be less than or equal to Qx. So why is this so? This is so because if P is 1, then we have that if P is 1, then we have that V minus 1 is 0, which is less or equal to Qx, because we already have that Qx is greater than 0. So that is satisfied. And if D minus 1 is greater than Qx, then it will mean that D minus 1 belongs to the set S, and that will contradict the fact that P is the minimum of S. So D minus 1 is better than Qx. Therefore, what do we have? What we have is therefore, therefore, Qx is really less than P because P is the minimum of this set, meaning that P is bigger than Qx. And P bigger than Qx is the same as saying that Qx is less than P. And this B is nothing but E minus 1 plus 1. So I have that this is Q minus 1 plus 1. And this P minus 1, we've already seen that P minus 1 is less or equal to Qx. So this will be less or equal to Qx plus 1. But remember that here we have that Qy minus Q into y minus x is greater than 1. So if I use this fact here, I'll get that this one is still less than Q into y minus x. And that will give me that this is less than Qx plus Q into y minus x. And this is nothing but Ux plus Qy minus Qx. So we see that this Qx will cancel this Qx. So what we've gotten is therefore that Qx is less than P, which is less than Qy. Remember that Q is a natural number that is bigger than this. As this is a natural number, I can divide this 2 by Q to get that this implies that X is less than P over Q, which is less than Y. So what does this mean? E is a natural number, Q is a natural number, P over Q is therefore a rational number. Remember that the set of rational numbers is not about the connection of only a vacuum, so that PQ belongs to the set of integers, and then Q is not equal to 0. And we also told that the set of integers is the set of natural numbers, the set of the subset of the set of integers. Therefore, what this means is that if we set so set it R equals this P over Q, we obtain that R belongs to the set of rational numbers and the x is less than r less than y. So what we've achieved is that if x is bigger than 0, then and we know that y is bigger than s, then we've achieved getting that there's a rational number between x and y. The next case is what we shall call case 2. In this case, we shall assume that x is less than 0. Here, case 2. Suppose x is less than 0. Then minus x is greater than 0. And we again apply the Archimedean principle that therefore there exists a certain k in the set of natural numbers so that k is bigger than minus x. K is bigger than minus x. This implies that k plus x is bigger than 0. Thus, we obtain that 0 is less than k plus x, which is less than k plus y. Because remember, we are assuming that x is less than y. That's given. So, what does this mean? Thus, using case, what we obtain in case 1, we obtain, say this is greater than 0. These are the turned us to the case where this is bigger than 0, less than k plus y. So using case 1, we obtain that there exists a R naught in the set of rational numbers such that k plus x is less than R naught, which is less than k plus y. And this is equivalent to x is less than R naught minus k, and this is less than y. So, setting s a pos. So let me use another variable. Set it to the pos r naught minus k. We obtain that nu is a irrational number, and then x is less than mu, less than y. This means, therefore, that given any two interfaces x and y, there exists a rational between them. So whether x is less than 0 or x is bigger than 0, we'll get that this holds. So what we've achieved is by giving any two random this. So that one of x is less than y, then there exists a rational number between them. Now, next, we shall also show that given any two real numbers, x and y, there is a rational between them. Now, next, given x, y in R such that x is less than y. Having shown that root 2 is in R and that 1 is less than root 2 from the one of the exercises we did above, meaning that root 2 is bigger than 0, we obtain that root 2 is in R for the place. Having shown that root 2 is not, the first thing we showed is that root 2 is not irrational numbers. Root 2 is in R, and in the process we obtained that 1 is less than root 2, meaning that root 2 is bigger than 0. So we obtain that x over root 2 and then y over root 2 are remainders so that x over root 2 is less than y over root 2 using this part. Thus, there exists, say, there exists R star in the set of rational numbers such that x over root 2 will be less than R star, and this is less than y over root 2. That is using the fact that we've shown that the set of rationals is dense in R. That is that between any two real numbers, there's the rational between them. And what this means is therefore that x is less than R star root 2, which is less than y. Now, setting R prime equals R star root 2, we obtain the R prime belongs to Q complement because this is not a rational number. And then x is less than R prime, less than y. This again shows us that between two real numbers x and y, there is an irrational number between, there is an imaginary number lying between them. So what have we achieved? This exercise has showed us that given any two real numbers, there is a rational between them. And given any two real numbers, there is an irrational between them. This therefore means that the set from the explanation I made using the concept of ecosystem and the species in a habitat, we see that the set of rational numbers is dense in R. We've seen that the set of rational numbers is dense in R, and also the set of irrational numbers is also dense in R. But importantly, the set of rational numbers is dense in R. Why I say importantly is because you recall that in one of our previous lectures, we were able to show that the set of rational numbers is countable. So what have we achieved now? What we've achieved is that the set of rational numbers is countable subset of R and also dense subset of R, meaning that R has a countable dense subset. So R, at this lecture, it shows us that in the lecture series we are putting up, shows that the first the first set we shall reach with a countable dense subset is the set of pre-numbers. If we go higher in the research, or if we do more advanced analysis, more advanced courses in analysis, we get to a point where we shall be talking about what we call separable spaces. And at that level, we shall define separable spaces as spaces that have countable dense subsets. That is to say that a space is separable if and only if it has countable dense subset. By this, we've seen that R, the set of universe, has a countable dense subset, and cross R is separable, meaning that the concept of separable spaces is not a backwards concept, because there is at least one that has that property. So what are we saying? The concept of separable spaces is a very important concept, and we should bear this in mind. That is why I am bringing up all these things at this elementary level, so that by the time we advance with it, many other things will be start popping up. I think this is a good place to call it a day in this particular, to call it a day uh, in this particular lecture. Hoping to see you next time. But remember, it will be good if we continue following the lectures we are uploading. Start continue sharing that others may benefit, and also as you are watching and sharing, also make sure you try to subscribe so that whenever we upload a video, you will be alerted that a new video has been uploaded. Thank you so much. We will continue the address to make sure that we make analysis as easy as possible. Thank you for listening.